Hello, my fellow 302 students. I'm gonna have to do this quick because I'm late for work, but let's see what we can do. Okay, first, today in class, we talked about dot products and the properties of a dot product. Okay, so first of all, dot products will always give you a scalar quantity. You'll never get a vector when you do a dot product. Dot products are commutative, meaning that they can go backwards or forwards. So it doesn't matter if you have u dot v or v dot u, whether they're negative or positive, doesn't matter. We have not talked about yet if it matters if it's negative or positive, or what a negative or positive dot product means yet. So bear with me on that. They are distributive, meaning if you have a u vector dot with a v vector plus a w, there's supposed to be a vector sign right there. It's the same as a u dot v plus a u dot w. So you just distribute there. That's simple. If you dot a product with itself, it's like squaring the magnitude. There's supposed to be another vector sign right there. Sorry. And we get that from the Pythagorean theorem. We're going to use this property in just a second. And if you dot with a 0, then it's going to equal 0. Okay. Then comes to this dot product equation. It's a theorem that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. Okay, how do we get that? It has to deal, here's the kind of the proof, it has to deal with the law of cosines. Law of cosines says, which is just a take from the Pythagorean theorem. It's just an adjusted Pythagorean theorem. C squared equals a squared plus b squared, but because it's not a right triangle, you have to minus 2ab cosine theta. So this is kind of the adjustment that it's not the Pythagorean theorem. So this is the law of cosines. This is what the law of cosines says. So let's look at a triangle of our two vectors and see if anything like that makes sense. So here's our triangle. We have our u vector here, our v vector here, and then that means that this vector in between them is going to be u minus v. In other words, we have an a side, a b side, and a c side. So what if we just plug this into our law of cosines equation, which would give us a u vector minus a v vector, and we're going to square it because it's like c being squared in our law of cosines equation. And then we have the vector u magnitude being squared. Why? Because it's like a being squared. Same with v, just like b being squared. Then we have minus 2, this is just part of the equation, the magnitude of u, magnitude of v, and or the norm of u, norm of v, times the cosine of theta. Notice this right here, this little section right there, is what we want up there. It's the same as this little section. So we don't want to touch that. We don't want to touch that. So what we're going to do is we're trying to use some properties here to solve these things. Okay, so first we have this right here. So there's a property though that says when I dots a vector together, I get that same vector. So can that go backwards? So if I take a vector and can I break it down to its dots? The answer is yes. So I can take this and I can break it down to a u minus v dot a u minus v. Next, I can do the same with these. So I have a u dot u with a v dot v. And then I just move down this section because I don't want to touch it. So what it looks like now is we've got this factors out to a u dot u minus a u dot v minus a v dot u plus a v dot v. And then these come down and this comes down. Okay, so what this is going to end up looking like, let me grab my marker again. What this is going to end up looking like is there's two u's on this side, there's two u's on this side. That means they cross out. Two v's on this side, two v's on this side. That means these cross out. What does this become? This becomes a negative 2 u dot v. Because those are the same thing, so it becomes negative 2 and it's u dot v. And they can go either way, it's commutative. And that equals this stuff over here. Negative 2 norm u vector norm v vector cosine theta. So 2's cross out. We have the dot product of u dot v is equal to u norm times v norm times the cosine of theta. And that's just saying the small angle between 0 and 180 degrees between these two vectors is what that cosine theta is. All right, real quickly now, we also talked quickly about the Cauchy-Schwarz theorem, either way, which it takes the theorem that we just proved and it puts that the absolute value of that, whether it's negative or positive, is going to be less than whatever this is. And he can do that because he just drops the cosine, because cosine can never be more than -1 or 1. So he's saying that these are going to be equal in that sense. Hopefully that makes sense. Something that was really interesting to me in this class, and I gotta hurry, but projection. Projection written by like a proj of u vector on v vector, like this, written like that, is equal to u vector dot v vector over v vector dot v vector times v vector. I don't know where that specifically comes from, where that projection comes from, but what it basically says is that if you have two vectors, v and u, it's like if u is being projected on v, it's like u's shadow on v. We see that. So the interesting thing is you can find this vector and you take y, because you can take u vector minus the projection of v on u. And that is an orthogonal or perpendicular vector to v. That'll come in handy, I'm sure, sometime. How to prove this, though, is super interesting because we know that, what was it? When you dot a product with something that is perpendicular to itself, perpendicular to it, it becomes 0. So when you dot this with, this is the equation for this right here, and you know it's perpendicular to v because you're going to dot it with v. And look back in my notes real quick. The projection, this is the projection right here. This is just an orthogonal vector that equals to this. So you know that this is orthogonal to the projection because then you dot it with, sorry, you didn't see my writing. You dot it with the projection, which is u vector dot v vector over v vector dot v vector times v vector. This dot product comes out to be 0. We tested that in class. So that was day 2 of lectures.